Bismillahirrahmanirrahim and Assalamu alaikum. My name is Yasir Mahmood and I'll be teaching you convolution neural networks today. And I've prepared this lecture from this Coursera course, and I'll keep the recording to less than 15 minutes because the free version of the tool that I'm using only allows the recording of that duration. Okay, so first of all, let me introduce myself briefly. I've done MSc Computer Science from PUCIT, MS from NUST, and currently I'm doing PhD from ComSat's Lahore campus, and I have over 12 years of overall teaching experience. Over 10 years of teaching experience was at the Virtual University of Pakistan, then one semester at the ComSat's Lahore campus, and from Feb 2023, I've been teaching at the University of Lahore. My research interests are computer vision, specifically AI-based analysis of medical images. I have won NVIDIA academic hardware grant in 2022 for my research project, and you can view the archive preprint of my research at this through this URL. And during my PhD, I've been able to establish collaborations with the leading researchers in my field, medical imaging. My collaborators are Professor Janming Liang from Arizona State University and Professor Anne Martel from the University of Toronto. And I am currently using the Compute Canada resources as an external collaborator of Professor Anne Martel, and my hobbies are to participate in data science competition and reading books. Okay, so before taking this lecture, you should have this prereq knowledge. So you need a basic understanding of how images are represented digitally and how they are processed, and what is a fully connected neural network, and its component parts, layers, and neurons, and what is forward propagation, and how different outputs of different layers is calculated through different activation function, what is the loss function, and how we calculate the loss, and based on this loss we perform back propagation, and during back propagation we update weights, and what are other hyperparameters like learning rate, batch size, optimizer, and number of epochs, etc., and what are the regularization techniques like early stopping. Okay, so convolutional neural networks or CNNs, they are very popular for the image data or videos, and they are based on convolutional layers, and what makes them very useful for the image data is uh, one of their main qualities is the translational equivariance. So that means that if our object of interest is at different locations within the input image, it will make no difference, and the CNN or the model will be able to detect this object regardless of its location within the image. So it, of course, it has other qualities as well. Okay, so although it was proposed in 1980, but CNNs got popularity in 2012 when AlexNet, which is a CNN, it won the ImageNet competition by a very large margin. So, although currently modern architectures which have proved very good and achieved very good performance on image or video data, but still like the vision transformers, but still CNNs are very important, and they're very important to learn because a number of other architectures are based on them, like convolutional GANs, UNets, capsule networks, autoencoders, and multimodal architecture. So it's very important to learn um, about the CNNs. Okay, so before moving on to the CNNs, let's perform image classification using the fully connected neural network. And as we know that a fully connected neural network, it takes features as input, and then it outputs its predictions. Suppose we have a 6 by 6 image, and it has three channels because it's a colored image. Let's say that we treat each pixel value as a feature and we input it to the neural network. We have this 3D matrix to represent this colored image, but first we'll need to flatten it. uh, by flattening it, we means that we will form a vector. We will declare a vector or an array of size 6 multiplied by 6 multiplied by 3 or 108, and then we will put the first row, six elements of the first row of the first channel, uh, in the first six positions of this vector. Then in the next six positions we'll place second row, pixels of the second row, and so on. And we when we have placed all the pixels of the first channel, we'll repeat this process for the second channel and then for the third channel. And once we have this vector ready, we'll input these features to the neural network. So this method has serious limitations. So it's not scalable. For example, if we have an image size of 12 by 12, then we'll have 432 features. For 250 by 250 image, we'll have 1,87,000 plus features. For 500 and 500, we'll have 1.5 million features. And by the way, it's not very uncommon to have an image of this size. 500 and 500 is quite a common size. For 1000 by 1000, we'll have 3 million features. For such a huge number of features or input features, will need a lot of computational resources to train this data. And of course, it's not feasible. So the solution is convolutional neural networks, which have the weight sharing, and I'll explain it later what is meant by weight sharing. And so it's basically scalable and almost similar, very similar computational requirement for images of different sizes. And so convolutional layer is the main component of a CNN. And let's dive a bit deeper into what is a convolutional layer. It's basically in a convolutional layer we perform a convolutional operation. So I'll give you an example of how we perform the convolutional operation. Suppose we have an image, in the left side, a grayscale image. So it has only one channel, 6 by 6 image, and we'll also need a filter. Now we have, suppose, a filter of size 3 by 3. You can have filters of different sizes. Suppose we have a filter of 3 by 3. So we will move this filter throughout this image, and will perform certain operation. So suppose, first of all, we'll place this filter in this top left portion of this image, this 3 by 3 portion of the image. We'll place the filter over here, and we will multiply the corresponding elements. So 1 will be multiplied by 3, 1 by 1, and this one will be multiplied by 2, then 0 will be multiplied by 7, 0 by 5, 0 by 0, and so on. And at the end we will sum up all these products. Now we get minus 5. We'll place this value here. This is the top left pixel of the output image. After that, we will move this filter one step or one column to the right at this position where we have green zeros. Okay, and we'll repeat the same process. We will calculate the value. This time it is minus 4. Again, we'll move the filter one column right. We get the value of 0, and to the rightmost portion we get the value of 8. Now we have reached the rightmost side of the image. We will move this filter one row down, and we'll start from the leftmost side of the image, and we will repeat this process here from this portion of the image, and we'll repeat this process until we will reach this location, the bottom right portion of the image. So this is our output image. Okay, so this is how we perform convolutional operation. So basically, this is a very useful operation, and this is the same filter that we used in the previous example. And this filter, when we will convolve this filter, it will help us detect edges or vertical edges in the input image. Let me explain it a bit further. Suppose this is the input image, and its left three columns have high values, so the image will be brighter here. Right three columns have zero values, so image will be darker here. And in between, so basically an edge is an abrupt transition of the pixel values. So the in between, here we have the edge. So when we convolve this filter over this image with this image, we get this output image, and it has on the left and right most columns, it has the values of zero, so image will be darker here, and in the middle it has high values, so image will be brighter here. So we see in the middle of the input image there was an edge, and in the output image the location where there was edge has been enhanced or has high pixel values, so image output image will be brighter where we have the vertical edges, and will be darker where we don't have the vertical edges. So this is called an edge detection or a vertical edge detection. So this is how, so if we consider a vertical edge as a feature, then that means that using an appropriate filter we can extract any feature that we want, and with the help of cnns we can extract very complex or high level features. Like if we have a face, then eye is a feature. If we have a car, image of a car, then wheels of these cars are high level features. Okay, so we have other filters as well. For example, this filter is used for horizontal edge detector, and these two are the variants of the vertical edge detector. Okay, so next important thing or concept is the padding. As we saw in the edge detection examples, that the size of the output image was smaller compared to the input image. So sometimes we have very useful information throughout the image. So the reduction in size results in the loss of information, and it will hamper our results. And sometimes we have very useful information on the edges of the input image. And as we saw in the convolutional operation, that the pixels that are on the edges, they contribute lesser towards calculation of the output image. So to solve this problem, to avoid reducing the image size of the output image as a result of convolution, we use padding. So this is the padding. So this is basically 2 by 2 padding. We have basically added rows and columns around the input image. Okay, and now when we will perform convolution operation on this image, and if we use appropriate size filter, the image size will not be reduced. So here the padding is 2 by 2 because we have added two rows and two columns around this. We can have different size padding, 1 by 1 or 3 by 3 if you like. So this is the formula to calculate the image size after padding. Here n by n is the input image size, p by p is the padding, and f by f is the filter. Thank you very much.